So welcome to this EFCE Forum on Energy. We are going to hear from 5 speakers, and then we are going to have a roundtable discussion on the challenges and opportunities in chemical engineering for a global vision on very important topic of energy. I won't take up very much of your time. I will just let the chair of the session, Vice President of EFCE, Jean-Marc Leland, to start with his talk and also introduction to the forum arrangement. Thank you very much.
Thank you very much, President. So today we have a special session on a topic which is very important for everybody in the world, which is a world topic, and also, of course, for chemical engineers. So only to give you a flavor, we have a first part which is devoted to some specific presentation. I will try to give you, I'm not really a specialist of energy, but I will try to give you where are the place of chemical engineering and what we have to do in that fact. Then after we have a presentation for more specialists in this area. We are François Maréchal from École Polytechnique Fédérale de Lausanne. Then a presentation which is devoted to biomass-based energy system from Fabrizio Bezzo from University of Padova. And then we have a presentation from UK with Richard Dalton, that everybody knows there, as a past president of EFCE from Energy Future Oil and Gas. And also we have the pleasure to have a presentation from June Wispelwey from US, which is Executive Director of ICHE. And then after we may have a roundtable discussion. So for the question, I think the best way to let the question you have to the presentation at this time, and we may have some short contribution of people from Working Party shares. We will present some slide with question or even participate to the roundtable. And then after, Gani will hand the system. So basically, the idea that we have here is to say that when you look at the Working Party and section of the EFCHE, we have 20 Working Party and 4 sections. And actually, we are not really any Working Party or section really devoted to the problem of energy, which is, from my personal point of view, a lack. So after this discussion, we will see the opportunity to have and to open a section. So let me go now first for my presentation. So, okay, I will try only to see that as much more an introduction. Maybe I am right, maybe I am wrong, I don't know. You are able to criticize me. And I was looking at what they call the management of the energy and what are the key roles of chemical engineers. When you look at the energy, you will look there at the supply chain. And you will see that it starts to get energy from the earth, oil, coal. And you will see that up to now we have multi-source of energy. In France, well known from the nuclear energy. But you have also wind energy, you have also solar energy. And then after you have a system to distribute and to transport through different type of networks. Of course, this energy, we use it for our process industry, manufacturing system. And then after, we have to deliver energy to the society, to the people, and to the manufacturing, to the factory, and so on. And more like that, you will see that now there is a part of energy which should be used, not too much, but should be used in what we call stationary mobility, so in the systems that we have in the today life. Traditionally, we can say that chemical engineering was really in the process industry, which is really energy consuming a lot. But also we know better than me that chemical engineers have something to do also in this area, and especially by the past petroleum and so on. And we see that it's a multi-source and for a multi-purpose. And actually we didn't know maybe what should be the type of energy that should be used in the future. For example, I make any picture about shale gas, which has completely changed the economy of energy on the last 20 years. So chemical engineers are involved in the process. They are involved in energy production with the energy production resource system. And also one difficulty that we have difficulties to store energy. You know that nuclear systems, they didn't store energy. And we have to make network around different countries in Europe in order to use all the energy delivered by the nuclear plant, which is not really a good thing. So there is some things for the storage. And in that case, we have to do a lot. And there is the use of energy, of course. If you look further, you will see that most of the time in the process industry, what the people do, they try to use less and less energy to be more efficient and so on and so on. So there is this very, let's say, process integration system. There is also process intensification, trying to maybe better for raw material used, for water used, for energy used, and so on. But in that case, what may happen, when you are very efficient there, and you get better and better, you have to think where I put the energy, when I use energy, what kind of energy I have to use. It's called what we call the mixed energy system. And now when you deliver and you manage a big manufacturing system, from time to time, during the day, during the week, it should be better to use gas or to use coal and so on. And then you need to have a very flexible system, secure one, because the most important is to secure your energy, and so on and so on. So when you look, chemical engineers, they have things to do there for a long time ago. Of course, here it's the DNA of chemical engineering, but by be better efficient there, we have something to do. And it has an impact on that way. And now it's not finished. Because what we have to do is to be efficient with energy, but also we have to use less material, less air, less water, less fuel coming from I don't know, using different kinds of energy. And also after we have to be able to have less carbon dioxide, and we have to remove it, we have to store it, you have to separate it from other gas, you have the problem of NO, NOx and so on. And you have to find new process material maybe to store energy. And at this time we didn't know really how to do. So in fact the system is very tricky because the chemical engineers now, they are involved from that to that, and now we have to deliver and to deliver clean production systems. And the society for that is very, very careful about that. And the problem of energy, it's a problem which is very tricky because if you improve there, you can be worse there. And if you use here a new type of energy, you have to see the incidence you have there and you have there. And also if your dispatching network is working well. So I think that chemical engineers have more to do than before. Now I have tried to make a mimic of what has been done. I think it was in a EFCE journal by Grossman or something like that. And to see, according to what we are involved in chemical engineering and what working parties are involved, where we are and where we have to do. If you look at the micro nano level to the top level supply chain, something like that. Here, of course, you have at the micro nano to find maybe new type of nanoparticle, nanotube of carbons to store something like that. And you have to make molecular dynamic simulation and so on, fluid dynamics. Then after at the meso level, people from material engineering and solids, they think to have special form or something like that in order to store energy or to be better in the battery for a car, because in the car you have the engine, but you have also the batteries. And when you look at the future electrical car, it's much more battery. And then after the macro, you need to have system more and more clever. And here you have the unit operation. And then to the flow sheet. That is the field of the basic chemical engineering. And we have moved from that way to there. And also in another way, which it's much more devoted to the people who are using supply chain or people from industrial engineering, with mainly two parts. One part is to look at not a plant, but a cluster of plants, and to be able to design and to operate industrial systems with mixed energy systems, industrial smart grid, in eco park, or in some other things. That's one point. The second point is much more devoted to industrial engineering. It's when you are, that is, let's say, much more devoted to what we know. It's chemical engineering plants, industrial parks, something like that. And then you have to think at the level of a country or to a level of a landscape, what kind of energy should be used. Wind energy, solar energy, coal system, thermal system, and then to take energy, hydrogen, something like that. And when you look at that, I'm sorry because it was not my computer, I'm able to hint at that, but that's really a tricky problem. And this problem, people from water management system, they have also to solve it. To pure water, to domestic water, and to also water which has been used, and so on. So we have to look at what these people has done, because they are also a network. But it's not so clever that much more rough, rustic network, but they have already done that. And when you look there, from that to that, I can tell you that all the working parties are involved. People from mechanical particle, people from fluid dynamics, people, of course, from unit operation, and so on and so on. People from mixing, people from crystallization, and so on and so on. People from solids. And of course, at this level, it should be people from flow sheeting, process simulation, K people, process system engineering. And at this level, it's much more people from process system engineering. And also people from economy, connected to industrial system and chemical engineering. So when you look at that, you will see that there is a lot of things to do. And to finish, I look at what we are doing in the laboratory of chemical engineering. And I can tell you that energy system is very interesting for collaboration. So in that, the next slide, you will not have any confidential part. I only remove that. But you will see that on the left, it's a partner at the academic level that we have in the labs. And you will see different kind of partner, people from the wood industry, people from chemistry, catalysts, solids, and so on. And here you have international collaboration. It's only to have a map of what we are doing the last 10 years. And you will see, of course, there is some people very important lacking, but you will see that there is a lot of collaboration with that. It means that the energy system, it's really a field for scientists, and it's open also the mind, and it's open to some other people, and should be able to establish very nice collaboration. So you know what is my conclusion. Chemical engineering first, so it was unit operations, then flow sheeting, and then now we move to the nano level, to the really macro level, even the level to have a global vision. And I think that chemical engineering, we have a lot of to do. But now, if you ask to anybody in the street, do you think that chemical engineering, they are involved in energy? Do you think that chemical engineering, they are able to help you to have a car which is, I don't know, less consuming, clean car and so on? You know what is the answer? I'm not sure that they think at chemical engineering. And I think we have to tell and to affirm that chemical engineering, it's also, we have to transform the raw materials, transform energy, and to have to add service to that for the society. So it was only to an introduction, and now I think I will let the floor to more specialists, and I will ask François to come to deliver some idea with better figures and something like that that I have. So I disconnect that, François, and okay. We have to remove that also.
Tu peux laisser la refermer.
Je referme? Ouais, ok. Ok.
Let it come. Okay, so I'm going to discuss about the role of chemical engineering on the energy transition, and my goal is to discuss a little bit. Is there a problem? So, seems that the microphone is.
Yes.
It's okay? Yeah, okay. Right, so my goal is to discuss about the energy transition and to discuss about carbon dioxide, biomass, storage and efficiency. In fact, I will perhaps start by the status. Status of today is this picture. So the picture of the energy consumption in the world. This is given by the World International Energy Agency. And what is important here is that we can see that first, 85% of our energy needs is based on fossil fuel. Electricity is only 18% of the energy that we consume. Industry is 30%. The people living and the services is 35%, and transportation, which is mainly based on oil, is 28% of what we receive. So it's of what we use and not what we consume, because if now we look at the efficiency, so for supplying 100, we consume 167, in which 85% is based on fossil fuel. And then I can take, and so, yeah, perhaps something which is also important is that 75% of our electricity is based on fossil fuel. Now I take the same agency, and they are giving us some perspective of what is the future. So we have to reduce our emissions from 2000 up to 2050. And what you can see is that there is they have identified a lot of different ways of reducing this energy consumption, and the major one is efficiency. So it's not changing fuels or whatever, but first we have to look at efficiency. And then the second dimension is integration of renewable energy and carbon capture and storage. So it seems that the solutions are at the level of reducing the demands and the needs, increasing the efficiency in the way we are using energy, and use synergies by system integration. And then looking at the integration of the renewable energy, something which is important is the fact that renewable energy are intermittent. So it means that we will have not only to supply the energy, but also to supply the power, and therefore we will have to store. And perhaps also we have to capture carbon dioxide, because our goal is to reduce the carbon dioxide concentration in the atmosphere. And I'm going to discuss about this. And the first thing that I have to see, is it possible or not? And this is the picture from the European from CEFIC, which is showing that even though the chemical industry wants to increase its revenue, which means that they have to increase their production, they have succeeded to reduce their energy consumption, so the intensity, in such a way that in an overall system they have reduced the energy consumption. Okay? And the challenge is the same for the population. So we would like that the people are more happy, they will need more services, more comfort, but they will be more people, most probably, and therefore we will have to apply the same formula. We have to be more efficient in the way we are supplying the energy services, so that at the end, the amount of energy will reduce. And so what is the role of chemical engineering? So the chemical engineering is somewhere in between the fundamental research that are going to help us developing technologies, technologies that have to be assembled to create systems that will supply products, that will supply services in an integrated way by trying to maximize the use of the renewable energy resources, taking into account the different pillars of the sustainable development. So looking at the environmental impact, looking at the economy, of course, and the society as well. So we know how to do it, and I give you one example coming from what we do in the industry. So when we are studying the industrial processes, when we are studying the industrial processes, we look at the process units and the way we convert the energy inside the system to produce products out of raw materials. This means that we are developing new concepts of processes, we're improving units and optimize the operating conditions. Then we do process integration, so we increase the heat recovery, so we create synergies inside processes. And then we say, okay, don't forget exergy, which means that we are going to introduce heat pumping. And then afterwards, don't forget how we convert the energy that we buy into the useful energy for the process. And then we introduce combined heat and power in the system. And we never forget about realizing the system, operating it, and finally have some information about the profitability of the system. As soon as we understand the principle of integration, then we can go one step further. We can think about integrating different processes one with the other, which is, again, well known from the chemical industry point of view. There are a lot of big industrial sites that have been developed, and mainly this explains the efficiency of the European chemical industry. So integrating processes one with the other, reusing waste, and perhaps also looking at the waste not only as a resource, materials, but also as in a form of a heat or energy resource that we can convert into useful energy. And there will be still, because the first principle of thermodynamics still holds, there will be still heat available. And now you will look at where we need heat at low temperature. Cities. We need heat at 20 degrees C to be heated most of the time. So there is a very nice way of valorizing the waste heat of the industry, and some of the waste heat is needed because it's coming from the heat of reaction, right? This waste heat can be used in cities. Now, what is the importance? So for example, this is one example here we have made on an industrial site, and what we can see is that we have been able to reduce by 40% the energy that was consumed, and therefore reducing the energy bill. Of course, there is an investment which is related. So this is the first step, and I would say that it is the state of the art of what the chemical engineers can do. But there are other steps. Can we convert energy in a much better way? And the answer is yes, we can combine technologies. We can combine a fuel cell with a gas turbine, with a chemical reactor that is going to convert methane into hydrogen or syngas. And if we do it in a clever way, we can produce electricity with an efficiency of more than 80%, more than 80%, okay? By capturing carbon dioxide, because the carbon dioxide is a byproduct of this process, right? So the key is optimize the reformer. So we need catalyst, okay? We need to design the system, assemble the different elements in the system, make them operate together. So there are mechanical devices, there are electrochemical devices, heat exchangers. Everything has to be assembled, but the answer is 80% efficiency with CO2 capture, right? There are big challenges that I have already explained, including the control, because we have a small device that can be started, shut down when we need electricity, okay? And if you think that the electricity is coming from the sun some hours a day, perhaps this is the solution for the other hours, okay? And there is another paradigm. It's a small unit. So it means that I'm going to replace a very big plant with a huge number of smaller plants. Smaller plants that can be then associated to a given place. And when I'm saying to a given place, it means that I can deliver the waste heat that I'm producing with. So in the, I had 80%, I still have 20, and those 20% can be used for heating purposes at 20 degrees C. Okay? So in this case, I have another very big opportunity. This is an intensification process, and something which is perhaps new for the chemical engineers is that the intensification leads to a new paradigm in the sense that the cost is not anymore related to the size, but it related to the numbers of units. And this is also something which is very important, because now the challenge will be to build the plants that builds the conversion units. And this is where the efficiency and the cost reduction will come. Okay, another important element here is integrating renewable energy. If I'm integrating renewable energy, I have to look at what are the sources. And the sources of renewable energy is the sun. The sun is producing the wind, the sun is producing the hydropower as well, but the sun is also giving us some heat, and we have plenty of energy available there, right? What is the problem then? Okay, the sun can be converted into heat, but then I will be in competition with waste heat. It can be converted into electricity, but then I have to do an energy management, which has to be not only intermittent with the days, but also an energy management which will be seasonal. 28% of the energy is consumed for transportation. So I have to find a way to take the sun and put it in the car, right? And this is also a very big challenge which needs storage. And then I can learn from nature. So what did the nature do? Nature did capture the solar energy and convert it into biomass, which is the way the nature is storing the energy that it receives from the sun. So I have to make those management. Another element which is important is that if I'm looking at the biomass, which is the way the energy is stored by nature, what we can see is that by definition we will have a co-production of carbon dioxide. And I would like you to remind this point that I will explain later on. When I'm talking about biomass, most of the people think about biorefineries. And biorefineries means that we have to look at the processes that have to be imagined in order to produce the product. But in reality, we do not need the product, we need the functionalities. And this is also something which is important. I don't need biofuel, because perhaps I will be able to produce the biofuel, to produce the mobility by electricity. Okay? But I need stored energy. And the problem of biomass and biorefineries is that it can become very complex. And it will ask engineers to work not only on the biochemical part, but also on the thermochemical part, which then will most probably go towards the fuels part, but also on the integrated part. And it's important to think integration. I give you just one example. This is a process that is producing ethanol from wood. The efficiency is 30%. It means that I have around 70% of energy that is wasted there. So most of it is in form of lignin, okay? I can burn the lignin, no problem. I can even burn the lignin with a much more efficient system. But I can also use a thermochemical process to convert the lignin into natural gas. And in this case, the consequence is that I have a process that is going from 30% efficiency based on the biomass up to 70% efficiency. Okay? Now something which is also important, 70%, where is the rest? If I'm taking this example here, I'm converting wood into methane. The efficiency when the process is optimized is 75%. So there are still 25% of energy available. And something which is important, on this 75%, or on 25%, half of it, more or less, is available at more than 200 degrees C. So why don't we just convert boilers into synthetic natural gas production plant using biomass, using the waste heat for supplying the heat for the industrial processes, and capturing carbon dioxide, because I have to remove the carbon dioxide for closing my atomic balance, right? So it means now I have a system that is capturing carbon dioxide, that is supplying heat to the industry, and that is supplying fuel for the applications, okay? Applications. Of course, I can burn wood and produce heat, but I can also take the heat, transform it into electricity, use the electricity for electrical cars, and therefore substituting the heat that I'm producing by the fuel cell, for example, and using the electricity for the car. And what you can see is that there is, in this case, a factor 3, right? Something which is difficult with biomass is the supply chain, and my colleague will present the challenges on the supply chains in the next presentation. The supply chains are going to introduce other burdens, so I have to look at the complete life cycle analysis of the whole system, including the supply chain, if I want to be efficient. And there are also challenges. The challenges are related here. So you can see here that we have different processes here, different configurations, and they have another scaling factor. So if they have another scaling factor, it will mean that the investment will more or less impact the specific investment. Okay, so it means that if I have a higher factor here, I will be allowed to go towards smaller processes. Okay, and that's what is shown in this figure. There is a compromise between the environmental impact, the profitability, and the size. So if I'm taking the best one, which is here, the lowest environmental impact is here, the highest is here, and you can see that the profitability of the highest impact is different from the one with the lowest impact. Smaller plants, lower impact, but lower profitability. So the challenge there is the intensification. And what you can see is that different configurations that are shown here have different slopes. Okay? Something which is also interesting here is that if I'm using one indicator for the environmental impact or another one, the order of the different plants will change, which is also challenging because it means that I will have to take decisions. Okay, and compromise. Storing electricity. We can do it with a battery if it is for some minutes or hours. It will be much more complicated when I have to do it for the whole year, storing the electricity from the summer and use it in the winter. And I have the feeling that the only solution that we have today is the chemical storage. And the chemical storage compared to a battery is a factor 10 in the amount in the volume that is needed for storing this electricity from the summer to the winter. I'm showing here a picture that we have generated for Switzerland. So this is the peak. This is the peak that we have in the summer. And it's an excess of electricity, so nobody needs this electricity in Switzerland. So we have to export it, and it will be at the same time as Germany will export its excess of solar electricity, and the same time as Italy will do. Okay, France is a little bit different, but they will have the peak as well, most probably. Okay, so it's about 8% of the total consumption that has to be stored from the summer to the winter. So how can we do it? One way of doing it is to use the biomass. You remember that I have carbon dioxide. So carbon dioxide plus hydrogen can be converted into methane. And the carbon is there when I'm converting the biomass into methane. So it means that I can add hydrogen in this stoichiometric formula and produce more methane out of the same amount of wood by integrating an electrolysis in the system. The potential is 0.5 kilowatt or kilojoule per kilojoule of synthetic natural gas produced. So it means that I can produce up to 1.5 kilojoule of synthetic natural gas out of 1.3 unit of biomass plus the electricity that I will produce. But something which is important there is that I have to have a flexible process, because the process will see the variations of the sun, of the excess of electricity, and will have therefore to operate in a different way in the summer and in the winter, because there will be this excess of energy that will be available. This can also be done, and again it's a challenge for the chemical engineers, in a closed loop. So what I can do is that if I have carbon dioxide and if I have hydrogen, I can produce, by the Sabatier reaction, I can produce methane. I can store methane. Everybody knows how to store methane. Okay? I can use the methane and convert it into electricity. I've shown you a unit with 80% efficiency that is capturing carbon dioxide. So it means that I can take the carbon dioxide that I'm producing in the winter when I need this excess of electricity, store it, and we know how to store carbon dioxide. It's not so complicated to have a tank at let's say 50 bar or 60 bar in the liquid form, so that I will be able to reuse this carbon dioxide in the summer when I will have sun available. Okay, so now I'm closing the loop, and the carbon dioxide is just a vector here. There is no other sources than the solar electricity that is produced by PV. Okay, the round-trip efficiency is 57%, which means that I have to ask myself, where is the rest? Okay, and the rest is waste heat. Okay, waste heat, electricity, people needs to be heated, 20 degrees C, so I have a big opportunity there. And for the chemical engineers, it can be done in different ways. I can introduce electrolysis and then afterwards do the methanation. I can do co-electrolysis with a solid oxide electrolyzer. I can also do biocatalysis and produce the methane with a biocatalyst, with a biochemical process. The impact is very important. I'm going, just then I will skip this one, because I would like then to introduce you how can we then supply this heat at 20 degrees C that we need in buildings. And one interesting concept is to use district heating that is using carbon dioxide. I'm distributing carbon dioxide in the liquid and the gas form. If I need heat, I'm going to take the gas form and I'm going to produce a liquid form. So I'm condensing the carbon dioxide. And I adapt the temperature level by using a heat pump. If I need cooling, I'm taking the liquid carbon dioxide and I'm going to evaporate it. Okay? And again, depending on the temperature, I can use a compressor which is a refrigeration cycle, in order to adapt the level. If I have the two sources at the same time, then I will reuse the waste heat in order to heat. So it's a synergy. So we have shown that it was possible to heat the city center of Geneva by using 20% or even less than 20% of the energy that is consumed today without changing the buildings. So 20%, right? So it's factor 5 to 6 in energy reduction. Now I can even improve the system because I can add the cars. So I can put the solid oxide fuel cell, which is a small unit. I can use it as a range extender in the car, okay, to produce electricity with 80% efficiency, stored electricity in a chemical form, and supply the mobility services. Okay, from this, yeah, I will be even able to produce electricity because I have a power plant that is more efficient than the more efficient power plants that I know today in the basement or in the parking. So if I connect it to the grid, it can become an electricity supplier. So if I combine everything, then I can also use the photovoltaics, produce the methane that will then be used in the fuel cells in order to heat, to drive my heat pumps that are in the system. And something which is interesting here, I have an autonomous system, which means that it is only based on the renewable energy that is available locally. I do not have to buy any energy from outside, which means that the risk is minimized because the risk is the investment. So the day I'm doing the investment, if the bank is reliable, then the system is operated for a long time. And this is my conclusion. So there is an opportunity of generating systems that are even sucking carbon dioxide from the atmosphere, because if I'm combining now the biomass that is available, and it's mainly waste biomass, for example, the waste biomass that we have in our food, that we can convert into methane, we can have a system that is going to sequestrate carbon dioxide using the solar energy, right? And using only investment. So I have here the way of reducing or of creating sucking carbon dioxide cities, right? And this will be my conclusion for the chemical engineers. So we have to learn to convert waste biomass, produce bioproducts and biofuels. We have also to look at develop processes that do CO2 capture, separation of CO2, that is recycling carbon dioxide. We will have to work on process intensification, and we will have to go towards the better energy conversion, looking at fuel cells, electrochemical processes, and chemical storage. And something which will become very important, and it's most probably a breakthrough, is that all those processes will have to be flexible and robust. So it means that they will not be operated at 100% of capacity all over the year, because the energy services are fluctuating. And don't forget to think about systems.
Okay, now the floor is for Fabrizio.
Okay, thanks very much. Good afternoon. The objective of this talk is simply to share some thoughts with you. I won't be very technical, in fact, just to discuss a bit about energy and specifically biomassing energy, how chemical engineering can play a role in that, and what we need to do yet. Well, in the last years, I'd say especially over the last 10 years, but not only, several contributions have been published, but also there have been many industrial projects with the objective of turning biomass into energy. And when I say energy, well, we may say power or fuels, especially liquid fuels. In a way, especially if we look at the literature, we, and I'm not saying chemical engineering, we may say science in general, we have demonstrated that everything is feasible. Take hydrogen, second, third generation biofuels, microalgae, and so on. Everything has been, in a way, shown to be economically sustainable, environmentally friendly, should be there. Unfortunately, especially with concern to biomass, I think that we haven't met the expectations. With some exceptions, like it or not, first generation biofuels, power generations in some cases, we are not there. In fact, especially the most promising technologies, the advanced ones, are not there. We don't see a lot of industrial deployment. And why is that? I mean, I think there are many reasons. Some are simply political. And, but in a way, I think that there has been an underestimation of a few things. One is probably the complexity of such systems and the fact that there was a lot of things we didn't know. Just a couple of examples. One that come from my experience. One is about microalgae. I don't know if you have any experience with microalgae, but apparently they are the ideal system when you talk about biomass, because apparently you can do whatever you like. The cell is all photosynthetically active. It means that the theoretical production is huge. Also, theoretically, they can store a lot of oil, so they are the ideal feedstock to produce alternative oil, to make biodiesel or whatever you like. But production costs are extremely high, and yield, actual yield, is highly disappointing, especially when you compare it with what you may get in a lab. And the point is that when you look at the system, you realize that it's extremely complex and is a true multi-scale problem. I mean, if you look at the space scale, you go from, let's say, quantum physics up to the size, the typical size of agriculture, so hectares and so on. And the same with concern to the time scale, from milliseconds to, again, seasons, years, what we expect in crops and agriculture. And that was one of the problems that, in fact, in a way was underestimated. Another example, talking about supply chains, for instance, ethanol. We have been working a lot, also our group, trying to design, optimize the supply chains, how we should grow biomass, transport it, produce it, convert it, and so on. But again, with the exception of the first generation, we don't see much. Second generation ethanol, for instance, well, there has been a lot of discussion. There are industrial projects, but not so much. And here probably one of the key issues is about uncertainty, volatility in costs. This is the price of corn over the last 15 years. Difficult to make plan. Uncertainty in biomass availability. Technology performance. Well, here, this is a biological process. Here you have, let's say, different instances. Apparently, everything is quite clear. But if you break down a curve, the blue one, for instance, that simply represents an average behavior, you have something like that, which again tells you that it is difficult to forecast. Uncertainty about technology competitors. Who are the competitors? The food industry, the oil industry, car makers, uncertainty in the regulatory environment, incentives, and so on, environmental impact. I mean, at the very beginning, the only environmental impact that was important was the greenhouse gas effect. Then, especially in biomass, people said that water was also extremely important. So carbon footprint, water footprint, okay, they're important, extremely important, but they are also different. The carbon footprint is global, the water footprint is local. Uncertainty in the social acceptance of new technologies and so on. And yet, we may also say that as chemical engineers, we have been moving in similar environments for quite a long time. In a way, it should at least sound familiar. Well, let's see, yeah. If we go back to microalgae, for instance, we also tried to set up a proper, we may say, chemical engineering approach and to break down all the key process, for instance, to describe the growth mechanism, considering the really nanoscale phenomena up to some metabolism and so on. And we were able to get some very nice results. This is a collaboration with Imperial College, and even considering extremely complex light dynamics, we are able to predict the actual behavior of the system in a pretty good way. And this was interesting because using that model, so we realized that many parameters, in fact, had a physical meaning. That means that they could represent specific reactions or behavior, for instance, of mutants. And we were able to predict in a quantitative way genetic modifications in a real system, and possibly also to optimize the operating conditions. Something we are trying to do now, and this is possibly the most ambitious things, is that to use a model to drive genetic modification so that we can get exactly what we would like to obtain. And for instance, in this case, we were able to show that some mutants that were extremely promising in the lab, mainly because they were grown at low irradiation, were well performing, for instance, let's say during the winter or during spring, but were exhibiting rather poor performance during the summer. So it was possible to do something better that we were used to. And going from there, of course, we needed to keep on thinking in a chemical engineering way, so to add mixing, to add the transport phenomena. Light transfer is something new in this case, but we can do it. Unit operation design, interaction with the environment, process flow sheeting, and also maybe weather modeling. This is also something we try to do. We used the model proposed a few years ago, and with a collaboration with INRIA in France, we used some weather input data to set up a control strategy for microalgae cultivations. And we were able to demonstrate that you could nearly double productivity using suitable control strategies. What about uncertainty? Also in this case, I think that in the chemical engineering community, there has been several important contributions, either, for instance, adopting multi-scenarios. And we also realized that by using these approaches and, for instance, considering uncertainty in the feedstock price and also in the values of the incentives, we were able to produce a forecast on a plant profitability, in fact on the supply chain profitability, which was not a single figure, but in fact a distribution. More recently, we have been working on technology performance, and by using some concept from stock market, some theory about risk and regret, we modeled the performance, the uncertainty in the performance of some technology for power production and fuel production, and come up with a different supply chain and production systems, depending, for instance, on the degree of attitude towards risk an investor may have. On the other hand, yes, chemical engineering is there. We have a lot of expertise, of skills that can be used, but we need more. For instance, I think there is a lot of key information that is still missing. I think we need to realize that energy, but talking about biomass-based technologies, is extremely multivariate. Depends on many factors. And if you want to represent them, we need proper data capable of describing everything is important. That is why I think that one field we needed to invest more is, for instance, in design of experiments, optimal design of experiments to get properly informative data set, and also to use more multivariate data analysis to exploit information from what we already have. To do that, we also need probably more effective and efficient technologies so that we can have targeted information, rapid generation of data. In the field of microalgae, collaborating with the Department of Biology as well, recently we developed a microfluidic platform capable of accelerating the generation of data, so that we realized that in about 1 week we were able to obtain the same amount of data that otherwise we would have taken about 45 days. And that is something important. And then we needed to change a bit more our way of thinking. My opinion is that we need to realize that reality is stochastic. And I'm not saying we haven't done that so far, but probably this should become the standard way of doing things. That will carry out, that will cause some numerical and methodological challenges, but I mean, that's fine. That's our job, I think. Probably we will need to introduce a different way of representing, in a way, results. One idea is to refer to concepts like the design space that has been used a lot in the pharmaceutical industry, especially recently, and realize that everything is a multidimensional space. So it is not just about productivity, not just about economics, not just about environmental impact, not just about the social impact or safety, but everything must be considered together. And then we need to work in a very interdisciplinary environment. In a way, we are lucky because as chemical engineers, we somewhat used to it. But now I think we need new bridges towards biology, agriculture, finance, social science, economics, at least when we talk about biomass. Of course, without forgetting what we are good at. And so to conclude, new technologies disclose new scenarios, challenges, of course, opportunities. Energy is an extremely complex challenge, and biomass is part of it. I have no doubt that chemical engineering expertise and competencies will be needed, but we will need to address new challenges in a proper way. we need to realize that everything is multi-scale, and also the results are going to be stochastic and multivariate. We need to understand that multidisciplinarity is always a must, and that probably we need a more effective way of exploiting data and producing data. Not a new science, probably in a way the usual chemical engineering job, but a bit more complex, at least. That's my idea. Well, thanks very much for your attention.
Thank you for this biomass system overview. Maybe you want the first. Okay. Thank you. So now, Richard.
Hello? Hello? Right. I need to be able to see that. Is that okay? Okay. Okay, thank you, Jean-Marc, and thank you for the invitation. The title, as you'll see, is Oil and Gas and the Contribution of Industrial Ecology. I'm actually going to say almost nothing about oil and gas, but quite a bit about industrial ecology. I'm Richard Darton, as you heard in the introduction. I'm at the University of Oxford, but I'm going to present 6 slides, of which 4 were given to me by Professor Clift of the University of Surrey. I have changed some of them a tiny bit, but mostly 4 of the 6 are his work, so I would like to acknowledge that straight away. And Roland, if you're watching this and I've made some mistakes, I do apologize. The mistakes are mine, not his. As I said, there will be 6 slides, and I know that a lot of you are already looking forward to the last one. However, I can promise you on slide 3 there will be an equation. That will give you something to look forward to. Now, we've heard, of course, already quite a lot about energy this afternoon. The society we live in, particularly in the Western world, has grown into the form it is really in the last couple of 100 years on the back of cheap and freely available energy. I know that at times there have been problems in that availability and price spikes and so on, but basically we are where we are because energy has been relatively cheap and relatively freely available. But we know that that's made a few problems, because with that energy we've made ourselves, particularly in the West, quite a nice lifestyle. We use a lot of stuff. We use energy to transform materials, make things for ourselves, and that's all very good for our standards of living. But as we now know, transforming a lot of stuff, materials, what the Dutch call stof, I'm sure they got the word from the English, but anyway, it makes some problems. You make a lot of waste, for one thing. And also, when you use energy, as we've heard, a lot of our energy is fossil fuel related. What was it, 85%? It's putting CO2 into the atmosphere, which is giving us a problem, as we know, with global warming. So there are some difficulties. So let's just think how we got where we are today, and particularly I'm going to be talking about manufacturing and using materials, what you might call stuff, stoff, the things we make things with. Now, I'm sorry, some of the lettering on here is a bit small. That was because it was Roland's slide. That's his small writing. Starting on the left-hand side, the start of this global supply chain with raw materials, we either grow them, wood, cotton, food, or we dig them out of the ground, minerals, water, and we regard those as virgin materials which go into our manufacturing processes to make things with. What we make eventually becomes what you might call stock. We all have stock in our own houses. The companies we work for have stock. The universities we work in have stock. This is the material, the stuff lying around that we use every day to give ourselves a good life. And just as a kind of help think picture in the background, when I talk about stock, just imagine something you have like at home, like a cupboard full of shirts or a drawer full of shirts or socks or something. That's your stock. Okay, we use the stock. I have a garage with a car in it. That's my stock of cars. I use my car every day. And so it goes on. But of course, that stock wears out, runs out, needs repair, needs replacement. And that's what we're talking about in terms of economy, because as soon as I get rid of my car, whatever I do with it, and buy another one, the whole process comes into play. And in fact, that goes for everything I personally use, all of us use, the companies we work for, and so on. So stocks are continually being used, and the supply chain works. And of course, the supply chain uses energy. Now, there's various things you can do with that stock. You can retire it, downcycle or waste. Waste, at the end of life, it gets thrown away and something happens to it. But preferably, you can remanufacture it. So you can repair it. If you have a washing machine that's broken, you can repair it. That's the remanufacturing loop. There's a bigger loop. You can take the materials and turn them into something else. That's the reprocessing, put them back into manufacturing, and that's loop 2. And by and large, this is of course a simplification, but it's a generic picture of how we, through supply chains, provide ourselves with things that we use, right? Another feature about this, of course, on the left-hand side, the start of the supply chain is mainly a global business. We're extracting, shipping stuff around the world. That's global. Manufacturing is partly global, partly regional. But by the time you've got down to the level of individual stocks held by institutions, by people, by companies, you're at a local level. Remanufacturing is mainly at a local level. Reprocessing is mainly at a regional level. And that's important. Now let's see what that means in terms of energy. This is the equation, by the way. I hope it's not too complicated. The energy we require for a particular service, the service offered by my motor car, the service offered by my shirt, keeping me warm, keeping me decent, my drawer full of shirts, 20 shirts, say, each one gets used, eventually replaced when it wears out, and so it goes on. The service is the clothing, if it's transport from a car or whatever. What I really want from that stuff, that material, is a service, something that I need. The service is D. The energy to give me that service is, if you'll easily be able to work this through and work out that it does, in fact, match, is a product of factors. The energy intensity of production, E over P, the amount of energy per unit of material that I need to replenish my stock, times P over S, the flow required. The bigger the flow for the stock, the more energy I'm going to use. And S over D, the product service intensity, which is important. How much stock do I need to deliver a service D? Just think of an example, for example, Imelda Marcos. How many pairs of shoes did she have? I can't remember. It was over 1,000, wasn't it? How many pairs of feet did she have? Yeah, you see what I mean? If you're a poor child in a third world country, you probably don't have shoes. most of us are somewhere between the third world child and Imelda Marcos, right? I'm not going to ask, it'd be quite interesting to go round, how many pairs of shoes? But I wouldn't like to embarrass you. But that's what product service intensity is. I have to confess, my family nowadays have an astonishing number of cars because all my children seem to need cars. But that's the type of thing. How many of something do you need to keep you satisfied that you're getting the right service? Let's pick this apart because we're here to talk about energy. Let's pick it apart in terms of energy. Here we've got our global picture. I've showed it again just to remind us that we're talking about this extraction, processing, manufacturing, utilization, reprocessing, and the two loops. The energy that we use in keeping this lot going is the remanufacturing energy when we go into this little local loop, plus the recycling energy, that's the rather larger reprocessing and recycling loop, the primary production of the manufacturing and the extraction supply chain, the operation energy, which we're not going to go into in detail, but if you think in terms of shirts, that's the washing energy, the ironing energy, for those of us that do ironing, or whose partners do the ironing for us, I have to say. Or, for example, obviously, if you're driving a car, the operation energy will be the energy that you need for actually, the petrol, which is a substantial amount for a car. For a shirt, it's probably not so much. So that is the energy that you need to keep this lot going for the flow P, keeping the stock S. And you'll see that all of it, except for the operation energy, has the factor P in. Clearly, if you want to reduce energy demand in society, you want to use less stuff, because each kilogram of stuff that you use has to be processed, reprocessed, recycled and disposed of, etc., etc. So you get the point. Using stuff involves using energy, and it works this way. So what we always need to do, minimize the amount of stuff to minimize the amount of energy. From that last list, we can then prioritize looking at the whole economy. If we want to reduce the amount of energy we're using in the amount of stuff, the amount of materials that we're making use of, what do we do? Well, the obvious thing, the first thing is extend useful life. Because down at the bottom, I've repeated this, the flow is roughly equal to the stock divided by the residence time. Okay, providing that the stock is not changing. In a steady state, this would be absolutely true. So the obvious thing to do, if we allow our shirts to remain in our cupboard for twice as long, we only need half as many bought over a lifetime. You see how it works. We then use less stuff. So we make things last longer, which mainly means buying better quality. Intensify use to reduce stock needed. We don't buy 1,000 pair of shoes, for example, right? We use things more intensively and we make them last longer. Those are the two important things. Increase the fraction of remanufacturing as opposed to recycling, or indeed making things from virgin material. Now, there's a lot of talk at the moment about the circular economy. And if I go back, you'll see there are two loops in here. Both of them could be regarded as the circular economy. But those loops actually have quite different characteristics. Mostly, by far the better loop is the remanufacturing loop, because it uses much less energy and much less material. Have things mended locally, and that is significant for the shift in business between global type businesses and local businesses. increase the proportion of reprocessing, sure, rather than using virgin material. Reduce inputs to manufacturing, because that's where a lot of energy goes. Reprocessing, remanufacturing, and finally, bottom of the list in terms of importance, in terms of effect, which is what a lot of chemical engineers actually spend a lot of time doing, so we're concentrating actually on the wrong things, is reduce inputs to primary production. It's quite interesting to think that we've heard a lot about what chemical engineers do. It's numbers 5 and 8 on this list of priorities where many of us spend a lot of time. That's not to say that it's not useful and important, but it's perhaps not the areas that are really important. And we already had an example mentioned, I can't remember by whom now this afternoon, about, I think it was Jean-Marc said, if you ask the man in the street, what are chemical engineers doing to make your cars more energy efficient or something, and they would, I think, shrug their shoulders, and they're probably right to do so, because we're not working at the important end of the business, which is how do you make your car last twice as long, not how do you get 5% better fuel efficiency from it, although that's important as well. Okay, so the final slide, I'm going to have a couple of examples. I fitted them all on one slide. This is the last slide. The first one is called the Primark effect. I'm sure you all know what Primark is. You probably all shop there. This is the opening of the Primark in Oxford Street in London in 2008. People were fighting to get in. There are 2 policewomen here on the left-hand side of the picture who were there to try and keep people out of a shop. Isn't that amazing? To try and control the flow and make sure that public order was kept. Primark is a very successful retailer whose selling characteristic is that the material, or that the material that they sell, is relatively cheap. So they're selling on price. These are photos from the Daily Mail. The only time I'm likely ever to cite the Daily Mail, I think. For those of us who know the newspaper, you'll understand why. So the Primark effect was noticed after the growth of retailers like Primark. Primark's not the only one. There are a number of others selling cheap clothing. And what was noticed was that over a 5-year period, the growth period of Primark in the UK, municipal waste tips saw the proportion of textiles being thrown away by households rise from 7% to 30%. Now, when you read if you look on the web at the Primark effect, you'll see a whole lot of stuff written by journalists saying, of course, the cheap materials used by Primark are difficult to recycle. I personally don't think it's got anything to do with that. The fact is that the residence time of a Primark shirt in your drawer is about a quarter of what it would be if you bought from a full price manufacturer, who would charge you, by the way, about 4 times as much. So if you spend 40 euros on a shirt in a store, a good quality store which will last you for 2 years, and then you spend 8 euros or 10 euros on a shirt which you throw away after 6 months, this is what happens. If you have the same stocks of shirts in your drawer and they're lasting a quarter of the length of time, you're throwing away 4 times as many, aren't you? This is stocks and flows, something which is familiar to industrial ecologists and, of course, to chemical engineers. It's not rocket science, but it is very important science. If you're in the waste business, this is not a trivial matter, and it's not, of course, I'm talking about clothing, but it applies to everything we use and throw away. By the way, don't get me wrong, I'm not against cheap clothing, providing it's ethically manufactured, ethically disposed of, and the full costs of manufacture and clothing are falling on the people who are in that supply chain. They're not exploiting, for example, free discards. I don't know what it is in the rest of Europe, but most places in the UK, you can throw things away on a municipal tip without paying for that per garment. You pay a fixed charge however much you throw away. And there's a question of whether that's a good idea, but okay, that's a bigger discussion. Let's get back to oil and gas, where I think I should have been, and this is the very last, so we're there. Here's another stock, a stock that is causing us a lot of problem. It's the stock of carbon dioxide in the atmosphere. This picture, the black line, shows business as usual, modelled by a group led by Lowe a few years ago now. And this is business as usual up to the year 2100, shows the CO2 in the atmosphere going up from 400, just under, up to about 1,000, 1,100 parts per million. That's the prediction. The coloured lines show you their prediction of what would happen to the CO2 in the atmosphere if, at the start of each coloured line, human emissions of CO2 were reduced instantaneously to zero at that moment. So the green line, for example, shows you in the year 2010, which was the future when they did the study but is now 6 years ago, what would happen if all CO2 emissions stopped. And you can see that the lines come down very slowly, right? This, again, is stocks and flows, because the natural processes which take CO2 out of the atmosphere are very slow. In this particular case, the stock is not steady state. We can see that it's going up, and that's what we're worried about, of course. CO2 in the atmosphere flows out very slowly, and this is underlining the problem we're in. Once again, stocks and flows, absolutely crucial. So, just summing up, looking at whole economy features is quite important when we're thinking about energy. That's been said already this afternoon. We need to take a systems view of this. Very often, the science behind it is not that difficult. To be honest, you can do an awful lot. You can even model this on the back of an envelope, roughly. The main picture is what is really important, and that's not difficult to get a grasp of. We need to get chemical engineers into quite different parts of the business, looking at whole economy models, not just concentrating on technology, important though that is, but whole system modeling is also absolutely vital. And just remember that energy use is very much tied up with other resources, other materials at the same time, and you can't really look at energy independently of what you're doing in the whole economy with other materials. That's it. Thank you very much.
Thank you very much, Richard. It was very interesting, this industrial ecology approach. So, June?
Okay. Well, thank you very much, Jean-Marc. I only have 3 slides, and I actually think that it probably won't take me 20 minutes to go through them, but the last time I did this presentation for my staff, we actually took an hour, so there's a little bit of there may be some questions, and I'm really happy to answer all of them afterwards. The United States has really taken a turn in their thinking on what needs to be done to solve some of the grand challenges of energy. And so what the Department of Energy has done, and this effort's going in a couple of other directions as well, is to form what they're calling a national network of manufacturing innovation. And this national network has been started a number of years ago. And as you can see towards the left of this very busy slide, there have been a number of institutes started up. There's one on the grid called Power America. There's NextFlex on America's flexible hybrid electronics manufacturing. There's one on photonics. There's one on advanced composites. A new one was introduced this summer on smart manufacturing. And so this year, the Department of Energy in the United States put out a call that I would say was right in the center of what chemical engineers do. It was the challenge for chemical engineers, if ever there was one. And I think it came about because, 10 years ago, I don't think we really saw the U.S. as building chemical plants much anymore. Maybe one or two here or there, replacing what we had, but there really wasn't a very vibrant chemical industry of the future. And then shale gas changed all that. And so the Department of Energy said, we really like this. And the president's office said, oh, we really like this too because it's creating jobs in the United States. And so these national networks for manufacturing innovation really have the opportunity to do two things in the United States: create jobs and improve energy efficiency, which is what the Department of Energy likes. And so they decided to put a call out for a NNMI on process intensification, specifically actually on modular chemical process intensification. And the purpose was to improve the energy efficiency, reduce feedstock waste, increase scalability, and improve manufacturing productivity. Looking at what process intensification does of merging particular unit operations, and then also looking at this sort of scalability, the scale-out question. So looking at modular components, reducing size with that scalability. And then lastly, what they said, and they actually looked at a lot of what was going on in Europe, and they said, boy, one of the things we think is really important is education. So education was key to this. And so they put out a call for proposal to receive $70 million worth of DOE funds over 5 years and the way that the DOE works in the United States is you don't get money from them unless you do something called cost share. And what they wanted on a cost share is a one-to-one basis. But we knew going in that it was more than that. And when I say we, so the AICHE really decided this was a pretty interesting proposal. And being the home of chemical engineers, we thought, well, this is something we think that we can help with in terms of getting the groups together. So we decided we were going to go for this, and we were going to try to get a very big cost share number. So the next slide, let's see if I can find page down here. Page up, page down. Okay. The next slide shows exactly what DOE was thinking, because they had some specific areas that they really had given some thought to. First of all, the energy intensive areas. And in the United States, that's chemical production, refining, pulp and paper, and metals. And so those were the areas of applications that were energy intensive. They also thought, this modularization component, that might work really well where you have decentralized manufacturing. So they looked at it for shale gas, for carbon capture, for biorefineries. And then they also said, and we have some other problems in U.S. production. Nuclear waste is one of the areas, and so they threw that in there as another application focus area. They also threw in food, because they know that food is actually a fairly large, can be a large consumer of energy, but it depends on which one. And then they said, okay, and we think you need to do this by modular manufacturing, by improving the modeling and simulation tools, and looking at other cross-cutting technologies, which are really those unit operations. And it's not only process intensification in terms of combining unit operations. They said, we want you to look at different heat inputs and all sorts of different things. And they did this in a very long document. And then, as I said before, and they said, and we want education. We want education in the undergraduate level. We want education of our workforce. We need education of the public. So they did all that. And they had a lot of metrics. As a matter of fact, they had 14 metrics to, that whatever group wins this proposal is going to need to meet. And it had to do with this energy usage, energy savings, efficiency improvements, CO2, scale out, education. I mean, it was a whole host. And they said at the end of the 5 years, when the DOE funding goes away, that industry has to sustain this. This has to be self-sustaining, which, if you did the math, $70 million divided by 5 years, that's a lot of sustaining for an industry that in the United States has really paid for very little of this work. It paid for very little of this work because the United States hasn't needed to do it. I mean, I see a lot of work that's been done in Europe, and it's been done in Europe because Europe hasn't had such cheap natural gas. And that cheap natural gas has in some ways made the United States a little bit, happy. But it could be happy in a bad sense in terms of in 5 or 10 years to maintain its competitive advantage. So the DOE was very strong on saying, okay, at the end of those 5 years, it needs to be sustainable. So what we tried to do was to put together this institute and save and meet these savings. So we have a huge ability to educate people, so that was one of our strengths. And we also had to choose projects. So we gathered a group of 34 universities, 75 companies, to come together to give us the best projects that we thought could meet the DOE metrics. And we did it in a number of different ways in terms of how we strategically looked at those projects. To be able to save, as you can see, the metrics at the top there. And we covered those 5 application areas, which really were the 3 most energy intensive ones that we took were chemicals, chemical production, refining, and pulp and paper. We really had a hard time, by the way, with metals because metals is so different. And then we gathered 77 national labs, 9 other nonprofits, looking at trying to reduce these and overcome these barriers. So the goals for this RAPID Institute, if AICHE is chosen to get it, will be to transform these technologies into manufacturing. So at the end of 5 years, you've really got to have sort of steel in the ground to create that advanced manufacturing workforce, to generate a supply chain. So for the modular pieces in particular, you have to have people that are actually willing to make that. And so we have contracting companies, we have small manufacturers, We have people sort of all the way up and down the supply chain that could potentially build the technologies that would be developed. Creating that sustained industrial network after the 5 years, and then becoming, and this is a very important thing for the United States, is becoming the globally acknowledged leader in modular chemical process intensification, which is going to be quite a stretch because I think that we're not there even close today. But we have, I think, with the DOE money of $70 million, we got a cost share out of industry, out of universities, out of state governments, out of local governments, out of other nonprofits of $264 million. And you can see here in this graph very nicely how, I mean, we've got participation from all of the major areas in chemical manufacturing in the United States. And these are also very small, and I apologize for that. But you know, you can see the national labs where the industry is, where the universities are, and our other non-governmental organizations. And so I think that with this amount of backing by the United States government, we can make an impact and reach the targets that the DOE has requested. But it's going to take a lot of cooperation, and it's going to take a lot of work by universities and by industry coming together to make this kind of challenge happen. Thank you.
Flavor from US, where you have always the capability to make a very nice network that we have much more problem to do in France and even in Europe. Well, let's say now we have seen 5 presentations. Now we will go for the second part, which should be much more devoted to question, and maybe also some intervention of chairman from the working party to ask questions and to tell what they are able to do. We have Jiri, which is specialist of process energy integration and so on. So I let now the floor to react, to have a question for the speakers, and also then after also the chairman from working parties to deliver some information at what you want. So for the floor, if you have any question for anybody. For me, I have one, but let the floor go before. It's okay. So if anybody has any question? I have one to start.
Okay, if you can use this one.
Yes. I have one to start. It's to Fabrizio. I know that biomass is a very complex system, and that there was a lot of difficulties with that. But when I was looking at you, I was thinking that it's a very difficult work for you to research on that, because it seems on a theoretical point of view that you have a lot of promising raw material, algae, and so on. And then when you start to research, it seems that you are some disappointed results. So maybe I make a mistake, or maybe it's a view which is pessimistic or a realistic view. Can you comment on that?
No, I think that probably reality is halfway. I'm not saying that my message was not that using biomass is a mistake, let's say. The point, I think, is that few years ago we thought that we were there. that getting ethanol from lignocellulosic material was an easy task, that using microalgae to make oil, diesel, and so on was just a question of few years of research. It is not like that. It is a longer shoot, I think. So we need more time, more research, but it is biomass. But I think that many of those issues can be extended to other systems. Uncertainty is not just a problem of biomass.
Okay, thank you. So, François?
Yeah, I would like to add a comment on this, because biomass is produced on the use of solar energy. And there is another way of producing chemicals using solar energy, is to convert it into electricity and capture carbon dioxide from the atmosphere. And the efficiency of this system, which is the photosynthesis, that's what the nature is doing, we can do it also industrially. So we can capture carbon dioxide from the atmosphere with an absorption or adsorption system. We can convert solar energy into electricity by photovoltaics. And today there are systems that can reach up to 40% efficiency in solar conversion. And at the end, if we compare the 3% of the photosynthesis efficiency to the combination of photovoltaics plus the chemical system is much more efficient and much more intensive than the nature. So, and which means then that we most probably do not have to grow biomass for doing the energy conversion, but we have to use the waste biomass, which will be produced anyway. And so, this then introduces different new processes to be dealt with the use of the sun.
Okay, I think that Jerry will react.
Yeah, I'm happy to continue. We are probably standing in front of the major revolution, because so far the transport is run by fuel, but it looks like this in 5, maximum 10 years, we will use electricity. And it will change a lot. It will change the perception of chemical industry. Chemical industry still will be needed, but not just burning biomass and burning oil. And what Francois said is the very true. I've got just 2 points. It doesn't need to be photovoltaic. I don't know if you've been in Morocco. They've got very nice plant which has got more than 500 megawatts, and it's using mirrors, and the rest is the classical heat and power plant in Sahara Desert, and it works surprisingly well. So there are many options. But another issue is we are talking about renewables, biomass, but if you go deeper in this, efficiency and reducing losses in transmission and conversion can save much more than so far we can generate by biomass. So I strongly believe that energy efficiency is a very important part of the game. It's not so much preferred by extensively growing industry, because business prefer to build, burn. Efficiency is a different story. But the numbers are showing it, that if we would like to really do something for cleaner environment, reducing losses, it's enormously important. Because biomass, well, it's fine by greenhouse, well, it's fine by CO2, not greenhouse gases. Because biomass burning generates NOxes, and a lot of NOxes. And they are very intensive greenhouse gases. And of course, we can remove them, but we can remove them by using energy, a lot of energy. And if you designed a biomass plant, biomass part is so big, but off-gas cleaning about is 3 times bigger and much more expensive. So those are some points for discussion.
So Richard?
Thank you. I'd like to start off with an advertisement, but you'll see it does have a connection to the last point. The advertisement is that the Sustainable Production and Consumption Journal is running a special issue, closing date next May, so you have a year to think about this almost, on sustainability performance measurement. We're interested in metrics. So if you're interested in this, see me afterwards and I'll give you a brochure. If you look at, that was the advertisement, if you look at the sustainability of an awful lot of industrial activity, you see it's not that good, and very largely because of carbon dioxide emissions. Now, in the transition to a better economy, we're having to manage this transition at a time when CO2 emissions are still largely not penalised. There's no significant CO2 price. There's very little legislation on CO2 emissions. It's starting, but it's not a major driver for industry. So my question really is back to the biomass people and indeed other renewable energy folk who may be here. Are we going to manage this transition without a floor price for carbon? Is it so that biomass can stand on its own feet and compete without somebody saying, right, the cost of emitting carbon is so much? Are we at that happy state, or are we still waiting for legislation and a carbon market to develop before it really works? And the same thing goes, by the way, for photovoltaics and a lot of the other renewables we've heard about. I generally like to know.
Thank you. Maybe you can. My question is for June. The proposal that you showed here, are there competitors for you for this, and are they also using process intensification?
There is one competitor that I know of. There may be others, and they would have to use process intensification and modular components to be able to meet the requirements from the DOE proposal. But I will say that as AICHE, we will, if a competitor gets it, we will do everything we can to help them in the ways that we can, because we feel very strongly that this has been a very good idea for chemical engineering profession.
I have it, so I'm going to use it. In Berlin, Philippe Tanguy made a good presentation 5 years ago, and he addressed the first time I heard it, the energy-water nexus. I didn't hear anything about it, François. And second question for me, which is a real pain, is to understand what is all about hydrogen. Right? In France, we have a lot of buzz about hydrogen. So I remember on chemical engineering progress, there was 2 pages. Yeah. First, it was hydrogen, a thermodynamics crime. On the right page, it might be interesting. So I think, as for me, for my pleasure or for my interest, I think hydrogen should be addressed, okay? At least for the French.
François?
Of course, hydrogen is in fact an intermediate product. The problem is that it is not distributed today. So it means that if you want to use hydrogen, you have to create infrastructure. And well, what I have shown, and it was for producing methane, but you can also produce Fischer-Tropsch fuels, methanol, and all those fuels can be distributed already today. and it means that it's most probably the hydrogen will be just an intermediate there, and then go back to the conventional distribution systems. And then with respect to your questions about the biomass and the cost of gas, what is interesting is that the hype on shale gas has created a lot of jobs in the US, has created a big move in the industry because they are shifting from oil to gas. The price has dropped because there is too much available, and of course it does penalize all the renewable energy penetration. And at the same time, they are going to increase the carbon dioxide emissions a lot, especially if they do not process the shale gas in the right way and they allow to methane to escape, or like it was done in California. So it's afterwards really a question of politics, so energy policy.
Fabrizio? Yes, and Jude.
Just a comment on the water energy nexus, that I think it is a really important one. And not only because we need water, say, to make energy, that's the case for biogas, for biomass, but also shale gas and so on, but we need a lot of energy to make water. I don't remember the figures exactly, but I think that about 30% of the power energy in California is used simply to make water. And so I think that the two issues are extremely connected.
So June and
I'd like to add something on the economics of biomass and that a lot. I think everything that was said was correct. But I think that what has not been said is that the economics on using biomass for some chemicals, especially the high volume sort of performance chemicals right now, if you can find a way to it, those economics are looking pretty good, even with oil at the price that oil is at today. And I don't believe that oil is going to stay at, $40-some a barrel. I think that oil is going to go up. It may not go up to 100 again, but I don't think for the economics for some of those fairly large volume chemicals that it's going to, I think that you're going to see a lot more production, like the Genomatica butanediol and the butane. So I would say that there is a brighter future than has been necessarily talked about with regards to biomass.
June, there is a...
Maybe, excuse me, I give you to, maybe this, what June said, maybe it's true also for algae. Algae, for creating very complex molecules. Excuse me, ma'am.
Thank you. So I guess I wanted to make a couple comments. One is, as somebody who has spent her entire career in industry, I will tell you that no disruptive technology ever comes in until it does something that nothing else can do, or the other part, the traditional way, is either no longer economically, politically, or environmentally, or most importantly, safety, and it's from a safety point of view, possible. It just doesn't happen. And the other question I had actually was for Professor Darton, because I have to tell you, I share my driveway with a very lovely millennial couple, and I keep hearing about how important the environment is to millennials. And the number of boxes they have on their driveway on trash day is not to be believed. So I don't know if there's an Amazon effect that you're going to be including. The other part is that there's a trend, I guess, in the States for people to deliver all the makings, fixings for a dinner so that you can put it together and claim that you made it. And from what I understand, this generates an incredible amount of packaging that the manufacturers are trying to deal with as a measure of their success. that they just have to deal with the fact that they have a tremendous amount of packaging stuff. I don't know if there's an Amazon effect, but I would say that free shipping is probably a metric that would not be considered sustainable because, like everything else in life, it's not free. It might not be a charge to the consumer.
Yeah. Yeah, it's quite amazing actually how many businesses there are that can initially make a lot of money by exploiting some feature whereby some of their costs are not fully paid by the business but are borne by society until society wakes up and sees that, and then they can be in trouble. It can take a very long time. It's taken about a century for society to wake up and realize that the fossil fuel industry is making use of the atmosphere like a dustbin. I mean, it's like a very large shirt drawer where you keep buying shirts and you never throw any away. That's why the CO2 level is just going up. Just think of the atmosphere as a shirt drawer into which we keep throwing shirts and never throwing them away. But you're absolutely right. New lifestyles very often, and progress very often throws up these rather strange results which take us a while to get around and behind. We have to be careful, though, that the older members of society don't just turn into a kind of moaning about the young. That's also not such a good idea. I think if we're trying to think of taking things forward, we have to be positive and say, how can we exploit and develop these new ideas of doing business, but more ethically and indeed more sustainably. By the way, sustainable packaging is a huge business and a hugely important one.
Okay. Is there any other contribution? Yes, please.
Actually, I would like to ask Fabrizio, because I got the impression that you worked for many years and that you got great results, and that in one moment that you were convinced that all the results were actually correct and that you're on the right way. But I was having the impression that in one moment simply you discovered something that makes you believe different. So what did you discover, and what techniques did you use to get the results?
Thanks for the question, but it's a bit complicated. Well, I've been working on, say, energy systems, especially on biomass, for quite a long time. It is not that I discovered something suddenly. It is simply that I realized that the initial optimism, I'm talking about energy, by the way, not about chemicals, so that's a different story, was due to an oversimplification of many things. But even now, I'm not saying that I'd exclude biomass from the potential feedstocks we may use to produce energy or fuels or so on. But we need to be a bit more careful, just that. Concerning the techniques, well, we might talk later, maybe.
Okay, so if there is any other reactions, or maybe the last one, because we need to close.
Yeah. It is related again to with respect to the costs of energy. Something which is interesting with the example I have shown for the district heating system, okay, is that the whole system is based on renewable energy that is available on site. So which means that there is no energy cost. The energy is coming for free. The cost of energy is made by the investment of the system. And we had the questions from the people that were involved in the project. Is it profitable? And the answer is yes. We have a 5 years return. And what is interesting is that the present system is not profitable because they have included part of the investment in the cost of infrastructure and not in the cost of the energy services. But this is very important at the level of when you consider the uncertainty of the cost. So if you apply the uncertainty analysis on the cost of energy, then you will see that the risk is always higher when you are based on fossil fuels. And the most robust solutions are always the ones that favor the investment, so more efficient systems, more investment, and less fossil fuel usage. And this is something which is also a very important message, because then we have to favor advanced technologies with respect to old and inefficient technologies.
Okay, thank you, François, for this contribution. So I think that now it will time to close this session. And first of all, before giving the Ghani conclusion, I would like to thank everybody, especially all the speakers that have made this session very interesting. Maybe more interesting than a lot of sessions that I have seen in any good symposium or congress, because there was different type of flavor, and also I was very astonishing by the way of US do the job, and especially how they are able to manage such a big network, because I think it's a lot of energy to do that, and they are able to do that better than we do again. And now let's Rafik to have some conclusion about this energy forum and the opportunity to have this energy section.
Thank you. I don't have any slides to use. No equations either. But I would say, first of all, thank you to all the speakers. I think you raised a lot of different issues. Management of the energy, integration, uncertainty, multidisciplinary, the industrial ecology, as well as how to set up a big project with big funding. So all of these are very important. And what I would say is that I should just say a little bit of why we wanted to do this energy forum, is that we do feel that there is this global challenge or problem, not of just of the energy, but energy, water, food, environment, because of the population increase that we are going to have and all the development that we need. And what I can see is that what has been said is that it's not a regional problem, it's a global problem. It requires multidisciplinary effort. It requires a lot of participation from different groups. So what we can do, at least from the EFCE, is that we start without the money. That means we form a section within the EFCE, which is a kind of a multi-topic, multidisciplinary group of working party or interested people who get together and try to advance the activities within a large area. So we wanted to see if EFCE should form a center section on energy, just like we have a section on sustainability, on food. So like that, we would like to see, wanted to see if there was sufficient interest and a critical mass of people who would like to do that. Looks like we do have, and those who are here and would like to help the EFCE form a section like that, please get in touch with me and Jean-Marc. We would like to set it up as soon as possible. But at the same time, we would like to also collaborate outside with AICHE and other also Asian countries. And the idea is that if we can form a critical mass, we go to the European Union to influence having project proposals on these topics. So then we can get together and not propose a 70 million kind of proposal, but maybe 10 or 20 million euro, involving a lot of universities and companies. So this was the objective, and I think this presentations as well as discussion was very, very interesting. And I thank you all for participating. Thank you very much.